All right, let's reinforce our theory with a few calculations that will look like what you'll see on your homework. All right, number one is going to test empirical probability. There are 3.4 million voters in Kentucky, 1.5 million Republicans. These are real numbers, actually, by the way. What proportion of Kentucky voters are Republicans? Notice here that I've used the word proportion because we are talking about large sets. How would fraction first? Remember, every probability is based on a fraction. Okay, well, a fraction, a probability should be the number of successes over the number of trials. So let's think this through in English first. What exactly would we consider a trial in this problem, and what would be a success? So all of the trials would be, we're going to try all of what? We're going to try all of the registered voters in Kentucky, 3.4 million of them. So therefore, what part of the fraction does that belong on? The bottom, okay? And 1.5 million of them are Republicans. That's what the question is asking for. So Republican in this problem is our definition of success, right? And that goes on what part of the fraction? Well, there's only one part left. It goes on the top. Okay, so we would write this as the number of successes, 1.5, over the number of trials, 3.4. And of course, each one of those is million, technically, but the millions cancel each other out. And then you can get particular with how you want to write that in simplest form. But basically, the millions cancel, and then you can shift your decimal point over. So it becomes equivalent to the fraction 15 over 34. Okay, now how would we convert that to a decimal if we needed to round to 3 places? So I pulled up the calculator here. Well, it's really easy to turn a fraction into a decimal. You can just divide 15 divided by 34, right? And by the way, if you didn't shift the decimal point, wouldn't you still get the same number? 1.5 million out of 3.4 million. Oh, good, same number. Okay, we need to round this to 3 places. So the first 3 digits are 441, and then we need to decide whether this decimal is closer to 0.441 or 0.442. I hope you remember your 3rd grade rounding rules. The 4th digit is less than 5, and therefore we would round this long, horrible string of numbers down to 0.441. So some of your homework questions will ask you to round, and they'll specify how many decimal places to round to, and the computer is pretty picky about that. So make sure that you're following the rounding rules carefully. 3, how would we write this as a percent rounded to 1 decimal place? Okay, well, that's easy. We just shift this decimal point 2 places over to the right. So 0.441 becomes 44.1. I don't know what I just pulled up here. 44.1%. Okay. B, if we select one Kentucky voter at random, what is the probability that it will be a Republican? So notice, again, I'm kind of being subtle with my word choices here, but in part A, I used the word proportion because we were talking about millions of people. And in part B, I'm using the word probability because we're only applying it to one person. So this one will really just be a question of credence. How confident would you feel that the next voter we choose will be a Republican? Well, remember, the best way to answer that question is to just borrow the proportion from the population that he or she is in. So 44.1% would be the same number here. Question number 2. 20 customers in the pet store today are looking for cats. 30 of them are looking for dogs. What is the probability that a randomly selected customer in the pet store today is looking for a cat? So it looks really basic, and I'm sure that many of you will get this right, but I also know that a lot of students miss this question at first glance. because they think it looks too easy and they hurry through it. So let's think this through with English, and I want you to think really carefully about who are the successes in this problem and who are the trials. And I'll give you a hint. If we write 20 out of 30, that would be the most common wrong answer. Because a lot of students would just see a 20 and a 30 and the word probability, and so they would just kind of instinctively put them over each other like this. But if we're doing that, we're not thinking carefully enough about what successes and trials mean. So in this problem, counting the number of successes is really easy. What is the probability that a customer is looking for a cat? Well, 20 customers are looking for cats, so that part is correct. But now let's think about the trials. How many people are we trying in this problem? Are we trying 30 of them? No, those are the people who are looking for dogs. We need to try everybody in the cat store, in the pet store. So if 20 people are looking for cats and 30 are looking for dogs, then how many are there altogether? 50, right? So this is a classic example of what I call a part-whole problem. You must remember that when you have a population that's divided into a part plus another part, if you put them together, you get the whole. And that's a very common step that we have to take in these problems that students often forget to do. Okay. Let me check my time here. All right, we're about half done with this clip already. This is going to be quite a lengthy lecture for this section. But that's okay because it's really foundational. So let's take our time with this topic. Okay, theoretical probability. Question number 3. If you roll a 12-sided die, what is the probability of rolling a 5? I wanted to get a little bit creative with my dice here. You might think there's no such thing as a 12-sided die. The dice that you usually see are 6-sided cubes. But I played Dungeons and Dragons when I was a teenager, so I know about these special role-playing dice. That's a 12-sided die there, and if you look carefully, you'll see that it does in fact go up to 12. Okay, I think this is called a dodecahedron. So if we roll this thing, it's got the numbers 1 through 12 printed on it. What's the probability of rolling a 5? Well, I think you would have to agree that all of these sides are equally likely. So this is just a matter of thinking through how many sides there are in the successes and the trials. So let's see. But it can never hurt to think these problems through using the word success and trial. What are the successes and what are the trials? So, and by the way, I think the number of trials is usually the easier one to find. Although in the last example, it was the successes, wasn't it? Okay, so what are the trials in this problem? The trials would be all possible sides of this die. So there are 12 of them. So would the probability be 5 out of 12? That would be the most common wrong answer again, because sometimes students just write down whatever they see on the page. But if you think about it, how many 5s are there? How many of these sides say 5? Only one of them. Okay, so the probability is really only 1 out of 12. There's 1 5 out of the 12 sides. Okay, what about, excuse me, what about a subjective probability question? Every time you eat a meal, either it will make you sick or it won't. Does this mean that the probability of getting sick from a meal is 50%? Sick or not sick? 1 out of 2. 50%? Does that make sense? No, because remember, this is a common fallacy. Events are not always equally likely. So just because there may be 2 possible outcomes, it doesn't mean that each one occurs 50% of the time. Some things are inherently equally likely, like dice, and some things are not, like getting sick from a meal. So I just want you to be aware of that fallacy, that difference. So no, the probability of getting sick from a meal is not 50%. In what zone of the probability spectrum would you expect it to lie? We haven't seen the probability spectrum yet. We'll see that shortly. But I basically what I'm asking here is, would you expect this to be very likely or very unlikely or close to the middle? And I think we would have to agree that we'd expect it to be a small fraction, one out of 1,000, 1 out of 10,000, I hope, something like that. Now, realistically, the reason we know that is because we've eaten thousands or tens of thousands of meals, and only a few of them have made us sick in our lifetime. So we know that the fraction will be pretty small like that based on our past experience. Now, we're only applying that best guess to this meal, but that's the best guess we have. All right, onward and upward.